All right, welcome to the next video in this series on classical mechanics. In the last video, we essentially described the location of a particle, a point P, with respect to some fixed origin in three different coordinate systems: Cartesian, cylindrical, and spherical coordinates. And in this video, we're going to talk about the velocity and acceleration of this point in two of those coordinate systems, Cartesian and cylindrical. And in the next video, we'll tackle spherical on its own. It is a beast and requires its own video. So before we get into Cartesian, I first want to talk generally about velocity and acceleration. So if we have a point P in space and we have some origin, then we know that we can draw a vector from the origin to the point P and we can label it OP. This is true for any coordinate system that we're in. Now let's suppose that this is just the location of the point at some point in time t. And let's say a little bit later the point may be moved over here. And this is the new vector that describes it. And we'll say this is OP at some time plus a small change in time. Then we know that in a small amount of time dt, so this is a small amount of time, we know that in a small amount of time dt, the particle had moved by an amount dOP, an infinitesimal amount OP, where this is equal to OP at that new change, or that new point, minus the original point. And so it stands to reason that the velocity of this point is this displacement divided by a change in time. Which, by the way, with the standard tip-to-tail method of vector addition and subtraction, that looks like this. Here's dOP, a displacement. So we took a displacement and we quote-unquote divided by a time, a very small amount of time. And that is the infinitesimal velocity, a small change in the particle's velocity or position. And so the acceleration, similarly to that, is just the second derivative of position with respect to time squared, which is just equal to the derivative with respect to time of its velocity. So acceleration is second derivative of displacement with respect to time squared, and it's equal to the derivative of velocity with respect to time. All right, so let's look at the Cartesian case. Now, before we get into this, remember what I said last video, that the basis vectors in Cartesian coordinates do not depend on the location of the point P at all. I can move P to be here or here, and the basis vectors are all going to be oriented the same way regardless of where P is. All right? So, if we have in Cartesian coordinates, we have a point P and a vector that describes its location, we'll call OP. Then we remember from the last video that OP can be written as x in the x hat plus y in the y hat plus z in the z hat, assuming this is z, x, and y. Then the velocity, as we just saw, is the derivative of this displacement with respect to time, which is the derivative with respect to time of this quantity. Now, if x hat, y hat, and z hat do not depend on the location of the particle, then it also doesn't depend on time. There's no time dependence of these basis vectors, right? The basis vectors are not changing in time. And so we can just write this as the derivative of the components with respect to time. Right? And here we're going to introduce a notation that you are probably familiar with, maybe not, depends on how you learned introphysics, the dot notation. Here, we're just saying that if I have a quantity q, and I take its time derivative, right, I'm going to write it as q dot. Now, it's important to note that the dot is reserved for a time derivative. If I take the derivative of q with respect to theta, I would write this as q prime, or maybe just leave it as dq d theta, but I will not write it as q dot. Dot is reserved for time derivatives. And likewise, the acceleration is just the derivative of that, x double dot in the x hat plus y double dot in the y hat plus z double dot in the z hat. That's it. That's all there is for Cartesian. All right, so next we're going to move into polar. Polar is a bit more nuanced, and the reason why is because r hat and theta hat are both functions of time. They do depend on the location of the point P, and thus, if P is moving through time, then so too are the basis vectors. So how exactly do we find their time dependence? Well, the first thing to do is to determine their theta derivatives. So we need to figure out what their derivatives are with respect to theta. So what is dr hat with respect to theta and d theta hat with respect to theta? Well, before we can do that, we need to first figure out what r hat and theta hat even are. All right? Well, we can easily figure this out using our special angles. So if this is y and x, and here's a point P, then we know that r hat points this way, and theta hat points this way. And if this angle is theta, right, then what can we say? Well, what we can say is that if theta were 0 degrees, then r hat is going to be equal to x hat, and theta hat is going to be equal to y hat, right? And if theta were 90 degrees, then r hat would be equal to y hat, and theta hat would be minus x hat. So what does this tell us? This tells us that r hat is actually equal to cosine of theta in the x hat direction plus sine of theta in the y hat direction, and theta hat is equal to minus sine of theta in the x hat plus cosine of theta in the y hat. Let's just make sure this works, right? If theta were 0 degrees, then we have that r hat is equal to cosine of 0 x hat plus sine of theta y hat, or sine of 0 y hat. Well, sine of 0 is 0, that's gone. And then cosine of 0 is 1, so we have that r hat is just equal to x hat when theta is equal to 0. And here, theta hat would be minus sine of 0 plus cosine of 0. Well, this would be 0, and we're left with theta hat is y hat. That's exactly what we expect. And if theta were 90 degrees, then cosine is 90 is 0, and sine of 90 is 1, so r hat is equal to y hat. And we have that minus sine of 90 is minus 1, and cosine of 90 is 0, so this is minus x hat. That's exactly what we would expect, right? Cool. So we have our basis vectors written in terms of our x and y hat, right? Well, let's take the derivative of r hat with respect to theta. What do we get? Well, this is equal to minus sine of theta in the x hat. Remember, x hat and y hat, they're not time dependent. Plus cosine of theta in the y hat. Well, this is equal to theta hat. Cool. And d theta is going to be equal to minus cosine of theta in the x hat minus sine of theta in the y hat, which is equal to minus r hat, right? It's this expression here, just with the minus sign. So now we have the theta derivatives. And I know what you're asking. Why theta derivatives? Well, here is why. If I want to find the derivative of r hat with respect to time, by chain rule, I can write this as the derivative of r hat with respect to theta times the derivative of theta with respect to time, right? And this is equal to what? Well, the derivative of theta with respect to time is just theta dot times dr d theta is equal to theta hat. There we go. And the derivative of theta hat with respect to time by chain rule is equal to d theta hat d theta times d theta dt, which of course is equal to minus theta dot in the r hat, because d theta hat d theta is equal to minus r hat. And so we now have the expressions of how the basis vectors change with time. Cool. Now, we want to figure out what the velocity is, and this is the derivative of OP with respect to time. But we know this is the time derivative of r and the r hat, assuming we're working in 2D polar coordinates and not cylindrical. However, if we were working in cylindrical coordinates, we know that this term right here would just be z dot and the z hat. But we're just going to work in 2D to make things simple. All right. Well, because r and r hat are both functions of time, this comes out to be r dot in the r hat, right, plus r in the r hat dot, right? Or written another way, r dot in the r hat plus r times the r hat d time. But we know what this is. This is r dot in the r hat plus r times, what is dr dt? Well, it's theta dot in the theta hat. So the velocity in polar coordinates is equal to r dot in the r hat plus r theta dot in the theta hat. This is an expression I highly recommend you commit to memory. We can write this v polar as v tangential, so it's a tangential component of velocity, plus a v radial component of velocity, right? The r dot, the r theta dot and the theta hat is a tangential component of velocity, because in polar coordinates, that corresponds to velocity about the theta hat direction, right? Hence it's in the theta hat direction. So if I have, say, a mass tied to a string, and it has some velocity, has a component of velocity that's going this way, and a component that points inwards. So maybe I'm getting weaker and weaker with how I'm spinning it in a circle. It's maybe going to spiral in, spiral in, spiral in. And this first term here corresponds to the velocity in the tangential direction. And the second term here corresponds to the velocity in the radial direction, which is this way. Now, right? In the special case of a circular trajectory, so we're assuming that r dot is 0, right? The radius isn't changing. We have that the velocity is equal to r theta dot and the theta hat. So this is a circular trajectory. Trajectory. R theta dot and the theta hat, which we're going to rewrite as r omega in the theta hat. Here, omega is theta dot, and it's the angular velocity. And this is an expression you're probably familiar with, right? You probably remember this from intro physics, which is why I bring it up, that v is r omega, right? But this is, this is like one of the cool things about this class. That is, in intro physics, you're like, oh, circular motion, I'm going to memorize this equation. But really, in this sort of physics, what you should be memorizing is this expression right here, the velocity in polar coordinates. And then thinking of the circular trajectory, the v equals r omega, as a special case of this expression when r dot, so the radius, is not changing. The time derivative of the radius is 0. Right? All right. So now let's move into acceleration. Here, we need to take the derivative with respect to time of the velocity, which is the derivative with respect to time of r dot in the r hat plus r theta dot in the theta hat. Well, we can break this into two terms, the derivative with respect to time of r dot in the r hat plus the derivative with respect to time of r theta dot in the theta hat. Right? Well, this first term, we're going to get the derivative with respect to time of r dot in the r hat direction by product rule. It's going to be r double dot in the r hat plus r dot times dr hat d theta, which is r double dot in the r hat plus r dot, and we know that dr d theta, coming back up here, is theta dot in the theta hat. Right? In the second term, well, this is a triple product rule, so we're going to get r dot times theta dot in the theta hat plus r theta double dot in the theta hat plus we're going to get r theta dot times d theta hat dt. Right? And once again, this is just the 2D case. You can easily generalize this to 3D by noting that the derivative with respect to time of z dot z hat is just z double dot z hat. But that's trivial. Right? But we know that this is equal to, right, this term d theta hat dt, right? We know, coming back up here, that's equal to minus theta dot in the r hat. So this is going to become, if I factor out an r hat and rearrange, and factor out a theta hat and rearrange, this is going to become r double dot minus r theta dot squared in the r hat plus 2r dot theta dot plus r theta double dot the theta hat. This, by the way, came from the fact that this is equal to minus r theta dot squared in the r hat, because d theta hat dt is minus theta dot in the r hat. All right, cool. So we have our acceleration in polar coordinates. It's acceleration in polar. Now we have a few cases here I want to look at. The first one is if theta is constant, so theta dot is 0, then the acceleration in polar is going to be, we're only going to have r double dot and the r hat, right? Because this is going to go away, this is going to go away, and this is going to go away. So if we're in polar coordinates and this particle is not moving in any angular direction, all it's going to be doing is moving outwards in the radial direction, right? It's going to be going out. Well, it should look like r double dot in the r hat direction. Its acceleration is only along the radial direction. And honestly, you might as well, if you want to, you can just relabel this as your x-axis, and this becomes x double dot and the x hat. It's the same sort of scenario. The second case is a bit more interesting. So r dot is 0 and theta double dot is 0. So it's uniform circular motion. So the particle, what r dot equals 0 means, the particle is not necessarily going out in radius or in radius. It's at a constant radius. And theta double dot equals 0 means that it's moving at a constant speed in the angular direction, right? So it's just moving in a circle. R is unchanged, and its velocity in the angular direction is constant. So our acceleration is going to simplify to what? Well, it's going to simplify to minus r theta dot squared in the r hat direction, right? Because this term goes away. This term, oh, that stays. This term goes away. These go away, and that goes away. They're all 0. But you may remember this from intro physics as minus v squared over r in the r hat direction. This is the centripetal acceleration. And this you used quite a bit in intro physics when you're solving any circular motion problem. But once again, this is a special case of the full formula here. So this is the formula you should commit to memory or memorize how to derive. It's going to come up everywhere in this class. And we're not going to be solving problems in classical mechanics that are just uniform circular motion. Sometimes it may reduce the uniform circular motion, but you shouldn't see a problem and automatically think, ooh, let me use minus v squared over r in the r hat direction. It should be that you just reduce the full expression down to its special case. And also, I want to point out that it kind of makes sense that this is in the minus r hat direction, because the velocity must be deflected towards the origin to maintain a constant radius. Yeah, that's it for this lecture. So we derived the velocity and acceleration in Cartesian coordinates, which is a very simple procedure. Here's the velocity, here's the acceleration. And in polar coordinates, it was a bit more involved, but we got it out. And I recommend you go through this derivation on your own to try to make sure you get it down. Once again, I don't want you memorizing v squared over r or v is r omega. Those, while they're true, they're very, very, very specific. And you should really focus on memorizing the derivation or memorizing the full expression of the velocities and acceleration, because those you're going to use everywhere. And you're going to see that when we start getting into Newton's laws and actually solving problems that requires us to write this down, we usually are going to write out the full expression and just take away whatever we don't need. So in a lot of cases, maybe the radius isn't changing, and so your r dot and r double dots go to 0. And you are probably going to be left with the centripetal acceleration equation. But once again, those are specific cases, and you should not focus on memorizing those at all.